Welcome to Module 2 of our course Indoor Environment and Building. In this module, we will shift from the foundations we covered earlier to practical strategies for achieving healthy and comfortable indoor conditions. We begin with ventilation strategies. Ventilation is the process of supplying fresh air and removing stale air from an indoor space. Its purpose is to control air quality, humidity, and temperature. There are two main categories of ventilation: natural ventilation and mechanical ventilation. Natural ventilation relies on wind and temperature differences to move air through windows, vents, or openings. It is energy efficient and provides a sense of freshness, but it depends heavily on outdoor conditions and cannot always guarantee stable air quality. Mechanical ventilation, on the other hand, uses fans and duct systems to actively control airflow. It ensures consistent air exchange rates and allows filtration of pollutants. Mechanical systems are essential in hospitals, laboratories, and industrial spaces where air quality must meet strict standards. Within these categories, different strategies exist. Displacement ventilation introduces cool air at floor level and lets warm, polluted air rise and exit near the ceiling. This creates a clean air zone around occupants. Mixed ventilation dilutes pollutants by supplying and mixing fresh air with room air. Each strategy has advantages depending on the type of building and activity. The goal is always the same: provide enough clean air for health and comfort while minimizing energy use. Lecture 2: Airflow distribution in buildings and industrial applications. Once fresh air is introduced into a building, the next challenge is how it is distributed. Poor airflow distribution can result in drafts, stagnant zones, or uneven temperatures. In office buildings, the design usually aims for uniform conditions. Ceiling diffusers distribute air across the room, while return vents remove stale air. In contrast, industrial applications often require specialized solutions. For example, in welding workshops, local exhaust systems capture fumes directly at the source. In clean rooms for electronics manufacturing, laminar airflow systems sweep contaminants away in a controlled direction. A key concept here is air change rate, measured in air changes per hour, ACH. Offices may require 3 to 6 ACH, while laboratories may need 12 or more. Distribution must be carefully designed to ensure that all occupants receive fresh air without creating discomfort from excessive air movement. Proper airflow design is not only about comfort, it is a matter of safety. In chemical plants or laboratories, poor airflow can allow dangerous substances to accumulate. In hospitals, improper airflow may spread infections from one patient room to another. Lecture 3: Smoke Control and Fire/Explosion Hazards. Another critical responsibility of indoor environmental design is protection against fire, smoke, and explosions. Fire produces heat, toxic gases, and smoke that spread rapidly through buildings. More people die from smoke inhalation than from burns. Therefore, buildings must include systems for smoke control. Smoke control strategies include compartmentation, where fire-resistant walls and doors limit the spread, and pressurization, where stairwells or escape routes are kept under positive air pressure to prevent smoke entry. Smoke exhaust fans can also be used to extract smoke from large spaces such as atriums. In industrial environments, explosion hazards must also be considered. Facilities handling flammable gases, dust, or vapors must comply with strict regulations, ensuring proper ventilation, explosion-proof equipment, and safe emergency exits. Regulations in the EU and Norway require detailed fire risk assessments for workplaces. This includes specifying materials with fire resistance ratings, installing detection and suppression systems, and training occupants in emergency response. Designing for safety in this context means thinking beyond comfort to life-saving measures that may never be used, but must always be ready. Lecture 4: Background and Basis of Air Conditioning. Air conditioning is the most common solution for controlling both temperature and humidity indoors. Let us now explore its basic principles. Air conditioning does more than cooling. A full air conditioning system, sometimes called HVAC, heating, ventilation, and air conditioning, can heat, cool, filter, humidify, or dehumidify air as needed. The basic principle is the refrigeration cycle, where a refrigerant absorbs heat at one point and releases it at another. This cycle allows the system to remove heat from indoor air and transfer it outdoors. In heating mode, the cycle can be reversed using a heat pump. But air conditioning is not only about temperature. Systems also control humidity, preventing both dry air problems and mold growth. They filter particles and sometimes include advanced purification systems to remove gases and microbes. In modern sustainable building design, energy efficiency is critical. Designers aim to minimize cooling loads by using good insulation, shading, and natural ventilation where possible. Air conditioning is then applied to fine-tune conditions, reducing energy waste. Lecture 5: Indoor Environment, Health, and Thermal Comfort. Air conditioning and ventilation systems exist for one ultimate purpose: to protect health and ensure comfort. We must remember that indoor environment directly affects human performance. High CO2 levels make people drowsy. Too warm an office reduces concentration. Too cold a classroom distracts students from learning. Thermal comfort, as discussed in Module 1, is not only about temperature but also humidity and airflow. Engineers often use indices like the predicted mean vote, PMV, to predict how comfortable people will feel in a given environment. A good design aims for conditions where most occupants, around 80% or more, are satisfied. Indoor environment and health are tightly connected. Poor environments contribute to conditions such as asthma, cardiovascular disease, and stress. Good environments support mental alertness, faster recovery in hospitals, and higher productivity in workplaces. Thus, engineers and architects carry a responsibility not only to design functional spaces but also to design for health. Lecture 6: Change of state of humid air. To design effective HVAC systems, one must understand the change of state of humid air. Air always contains water vapor. When air is cooled, its capacity to hold vapor decreases, and condensation occurs. This is why cold surfaces like windows often show water droplets in winter. Engineers represent these processes on a psychrometric chart, which shows relationships between temperature, humidity, enthalpy, and other properties. While we will not draw the chart here, it is essential for calculating cooling loads and designing dehumidification. For example, when moist air is cooled below its dew point, water condenses. This process is used in dehumidifiers. Conversely, adding moisture through humidifiers changes air from dry to more comfortable conditions. Understanding these changes ensures that systems can control both temperature and humidity effectively, preventing discomfort and building damage. Lecture 7: Different ventilation and air conditioning solutions. There is no one-size-fits-all solution for buildings. Different types of spaces require different ventilation and air conditioning systems. Natural ventilation is suitable for mild climates and low-density buildings. It uses windows, vents, and chimneys. Mechanical ventilation uses fans, ducts, and filters to ensure controlled air exchange. Hybrid systems combine both, using natural ventilation when conditions allow and mechanical systems when necessary. Centralized air conditioning serves large buildings with one system, distributing air through ducts. Decentralized systems, like split units, serve individual rooms or zones. In industrial applications, specialized solutions include fume hoods, local exhaust systems, and clean room designs. In hospitals, ventilation must follow strict zoning to separate sterile and contaminated areas. The choice depends on climate, building use, energy efficiency goals, and health requirements. Lecture 8: Natural and Mechanical Ventilation. Let us take a closer look at natural and mechanical ventilation. Natural ventilation is attractive because it uses little energy. It relies on two physical principles: wind pressure and the stack effect. Wind pushes air into one side of a building and pulls it out the other. The stack effect occurs when warm air rises and escapes through high openings, drawing in cooler air at lower levels. However, natural ventilation cannot always guarantee good air quality. It depends on outdoor wind and temperature differences, and it may introduce outdoor pollutants. Mechanical ventilation, by contrast, provides reliable and controllable air exchange. Systems can include filters, heat recovery, and humidity control. They can also be designed for energy efficiency by recovering heat from exhaust air. In practice, many modern buildings use hybrid systems, maximizing natural ventilation when weather conditions allow and switching to mechanical systems during extremes. Lecture 9: Field Investigation and Evaluation of Indoor Environment. Finally, theory must be linked to practice. Engineers must be able to evaluate indoor environments by direct measurement. The key parameters include operative temperature, which combines air and radiant temperature. Air velocity, to assess draft. Turbulence intensity, indicating fluctuations in airflow. Relative humidity. Pollutant concentrations, such as CO2, VOCs, or particulate matter. Measurements can be carried out with instruments such as anemometers, hygrometers, CO2 sensors, and thermal comfort meters. After collecting data, results are compared with design specifications and standards, such as EN 15251 or ISO 7730. This analysis allows engineers to identify problems, such as insufficient ventilation or high pollutant levels, and propose corrective actions. Equally important is the ability to work independently and in interdisciplinary teams. Indoor environmental quality involves architects, engineers, health specialists, and building managers. Collaboration ensures that solutions are practical, cost-effective, and health-focused. Lecture 10: Summary of Module 2. Let us conclude Module 2 with a summary. Ventilation strategies, both natural and mechanical, are essential for supplying fresh air and maintaining health. Airflow distribution must be carefully designed to avoid stagnant zones, drafts, or unsafe conditions. Smoke control and explosion prevention are life-saving design responsibilities. Air conditioning provides control of temperature, humidity, and air quality, forming the backbone of indoor climate systems. Indoor environment and health are inseparable. Good design improves comfort, productivity, and well-being. Understanding changes in humid air is vital for controlling condensation, mold, and comfort. Different buildings require different ventilation and air conditioning solutions, from natural ventilation to advanced cleanroom systems. Practical field investigations using measurement tools allow engineers to assess and improve real environments. With this knowledge, you now have the tools to analyze, design, and evaluate indoor environments. You can connect theoretical principles with practical applications, ensuring safety, health, and comfort in buildings of all types.